What I want to accomplish here is to clarify some instructions and to hit some types of examples that were not included in the other videos that I asked you to view. For the first example, the instructions are show an expanded form and evaluate. So our summation notation is we're going from n is equal to 1 to 5. The expression that we're summing is 2 to the n minus 1. So we plug in a 1, plug in a 2, plug in a 3, etc., up to and including plugging in the 5. That makes the last term 2 to the 4th, because it was 5 minus 1 for the exponent. This part right here, that's the show an expanded form. So when you see those instructions of show an expanded form, they want it written out something like this. The evaluate part is, well, what do you get when you actually do that math? So it evaluates to 31. So make sure that you follow instructions on when you should be showing expanded form, when they want you to evaluate, when they want both. Okay, second thing I want to do. What if you start with something that's in expanded notation and you want to write sigma notation? All right. Obviously, you need your sigma. You need to choose your letter for your index. I'm going to choose I here. The ones that you don't want to choose are X, Y, or Z. X, Y, and Z are going to be the traditional variables X, Y, and Z in regular, so to speak, algebraic expressions. You want to avoid those for your index. Normally, if you have the choice of where to begin, it's convenient to start with 1, but you don't have to start with 1, and I'll explain what I mean by that in a moment. When it comes to dealing with fractions, sometimes it's better to look at, rather than the entire value of the fraction, well, what's the pattern on the top, what's the pattern on the bottom? Well, the first term is a 1, second term is a 2, third term is a 3, so the top of the fraction is just I. Each denominator is 1 more than a numerator, or 1 more than the number of the term. And then the last number that we're going to be plugging in will be the 11. So the top of the fraction matches that, which also makes the bottom of the fraction line up as well. Now, in many areas of math that use summation notation, it's not always best to have that start with a 1. A lot of times it's more convenient to start with a 0. So one of the skills that you should have is to be able to change from one to the other. So what if we wanted to start at 0? Well, if we're starting at 0 and we're going to be producing the same number of terms, that means that we'd have to stop at 10. Now, whatever direction these guys go in, those guys have to go in the opposite direction. So what I mean by that is if both of those went down by 1, then both of those have to go up by 1. Or we can obviously write that as I plus 2 for the bottom. You can always check this to make sure you're correct. For the first term, we better get 1/2. So if we plug in a 0, we get 1 over 2, which is a half. The last term, which will come from plugging in a 10, better give us 11 over 12. When you plug in a 10 here and here, you get 11 over 12. Now, there probably wouldn't be a practical purpose to do so, but just to practice this skill. What if we wanted to start our counting at 2? So if the I starts at 1 to 11, if we make that go up by 1, the top has to go up by 1. And then whatever direction they go, the bottom, this part rather, goes in the opposite direction. So that means this would have to be I minus 1 over I. And again, if you're not sure whether you did that correctly or not, test a couple terms. If you start with the 2, plug it in, does it give you the first term, etc. All right, a little illustration of how this fits into the bigger part of math. When you guys get into Calc 2 or 3, depending on the structure of the sequence, when you get there, this is an idea of where all this heads. So what happens is you have common, what are considered now common to us functions, like e to the x, 1 over 1 minus x, natural log, sine, cosine. These guys are hyperbolic trig functions, which you'll learn about in the Calc 2-3 neighborhood. What happens is things that you wouldn't think of being connected to summation notation can be expressed in terms of summation notation. So what's going to happen at a future time, at a college, university somewhere, you are going to be learning how to deal with these types of things in summation notation. If you notice, all of these guys start at 0. So although the type of math we're doing right here, right now, it's usually more convenient to start with 1. Sometimes you need it to start with 0 in order to make it fit here. Other thing to take note of here, got a lot of factorials. Factorials, as some of you are aware of, have very practical places in counting and probability. They also fit into this part of the math world as well. So several different things you would have learning as separate topics where we are now all converge into one topic a couple math classes away. Alright, next thing we're going to address is something called a telescoping sum. So for this example, we have k going from 1 to 60, and this is the expression we're summing. K plus 1 quantity squared minus k squared. So what I did here is I plugged in the first few k's. What if k is 1? What if k is 2? What if k is 3? What if k is 4? And after you do those substitutions, you realize you have a negative 2 to the second from here will cancel with a positive 2 to the second from there. Then that will cancel with that. That will cancel with that. That will cancel with the next one that's not written. So we know that in the front of the pattern here, we're going to be left with that minus 1 squared. That's not going to be canceling with anything. All right, now the last three terms. K is 58, K is 59, K is 60. Here, you realize that the minus 60 squared cancels with the positive 60 squared. Oop, that's a typo. Minus 59 squared cancels with that. That cancels with the one before it. So the only thing we're left with here is a plus 61 squared. So with the one term from the beginning and the one term from the end, this thing evaluates to 61 squared minus 1 squared. Very often you would just leave it like that. It would be more common than actually multiplying it out, especially if that upper level of summation was like 600 instead of 60. You wouldn't be able to actually get a numerical value on your calculator. So either version of that final answer would be acceptable. All right, last example here. Something similar is going to happen. We're summing k is equal to 1 to 500 for the expression of cosine of pi k. So plugging in the beginning of the sequence, k is 1, k is 2, k is 3, k is 4, etc. We got the cosine of pi plus the cosine of 2 pi, cosine of 3 pi, on and on and on, and then the last couple at the end. Well, cosine of pi is 1, cosine of 2 pi, cosine of pi is negative 1, cosine of 2 pi is positive 1, cosine of 3 pi is negative 1, cosine of 4 pi is 1. What happens is these are going to keep alternating back and forth. The cosine of any odd pi is always a negative 1. Cosine of any even pi is always a positive 1. Then at the very end, we have the odd, the even. So we get a net result here of 0. That entire summation is equal to 0. Now, just as a quick what if we were going to 501 instead of 500, we'd have an extra negative 1 at the end, then the answer would be negative 1 instead of 0. For this particular type of sequence, we would just have to make sure that we correctly identify what cancels out and what remains. with the original version of 500, everything canceled out. With that what if at the end, there'd be a -1 left over for the final answer.